time. So hopefully I'll recover. Here I have a ball. If I have a ball up here, it has what kind of energy? Potential. So as it falls, what happens to its height? It gets less. So if I have less height, I have less potential energy, because that's mass times gravity times height. So that part works. So, but as it gets going down, 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 it's also getting faster, 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 because we have an acceleration due to gravity. So I'm getting faster and faster and faster, and as I'm getting more speed, I'm getting more kinetic energy. So by the time I'm almost hitting the floor, I have turned all that potential into kinetic. And we calculate how fast it's going. We actually find that the amount of kinetic energy we have right before it hits the ground is equal to the amount of potential it had up here. And so that just makes sense. This had height, that has speed. I've turned from one into another. But when it hits the floor and it bounces back up, it turns back into potential. But it only turned into this much potential, and I had this much potential to start with. So I'm missing some energy. So did the energy disappear?
No.
Very, very important. You never get magic energy from nowhere, and energy never magically disappears. Really, really important. So if it sure looks like it disappeared, where did that energy go?
Straight to sound.
2 places. One, when this hit the ground, it actually compressed a little bit and snapped back. That actually heated up the molecules inside here a little bit, and we'll learn more about that next week. But there wasn't a whole lot of heat. You're not going to feel this and say, wow, it's burning hot. But if you actually dropped it like 10,000 times and you touched it, you'd say, wow, it's warm now. Okay. But how many people hear it hit the ground? Okay, so if you heard it hit the ground and everybody in here heard it hit the ground, then that means everybody's eardrums wiggled, right? If I wiggled your eardrums, I did work on your eardrums. So if I did work on your eardrums, then that took energy. Now, if I could take this and I could make everybody's ears wiggle, and this would bounce back up to the same height, then where did the energy come to wiggle your eardrums? It would have to be magic energy from nowhere, and we can't get magic energy from nowhere, so does this make sense that this would have to get smaller every single time? Okay, so that other equation that I learned you on Monday when I wasn't here, and you guys were doing such a good job of not paying attention, we said the change in potential energy equals the change in kinetic energy equals the change in work. And basically this tells me is, if I increase my potential energy, I had to either decrease kinetic energy or do some work. If I increase my speed, I had to lose some height or I had to do some work. If I want to do some work, it's either going to come from speed or it's going to come from height. Does this make sense?
Yeah.
It'll make more sense if we borrow our friend Bob.
Oh, don't jump up.
Not again. Okay, so I have the little golf ball up here, right?
Yeah.
But if I take Bob and I hold him up here, does he have the same amount of energy that the ball had? The golf ball? Okay, so I would drop the golf ball on my foot and I wouldn't care. But Bob, I wouldn't want to drop on my foot. You could drop Bob on my foot if you only held him this much over my foot. Anything over that, I'm going to be sad. So that thing and this thing have the same height. They're going to have the same speed when they hit the ground, but they're not going to have the same energy. Which one would be able to do more work? Exactly. If I drop the golf ball on top of a nail, how far is that going to drive into the board? Very little. If I drop Bob on a nail, he's going to drive it into the ice. It's going to do a lot more work, right? So if this is sitting on the floor, so we're going to pretend the floor is level. If Bob is not moving, can he get any lower here?
No.
Is he moving?
No.
If he can't get any lower, then he has no potential energy. If he isn't moving, he has no kinetic energy. So does he have any energy at all?
No.
There's always somebody in the room that says, well, you could start him on fire because he has chemical potential energy. And yes, that is true, but we're talking about, okay, so he's got no speed and he's got no height, so he's got no energy in normal form. What do I have to do to give him energy? I have to do work. So again, if I grab up and I lift him up, I thought I was going to drop him on my head. If I lift him up, I just did, because I applied a force this way and he moved this way, so we had a force and a distance, so I did work, but now he has height, so he has potential energy, and I can drop him on anybody in the room and it would do work on your head, right? So the other thing that I could do is I could apply a force times a distance. That way, she likes broken ankles. So if I rolled him this way, then I increased his speed, which means I increased his kinetic energy. And that kinetic energy traveled across and then did some work on cutout. So if I throw it toward George, he actually stops it because that's smart. If we let it go, okay, we're not going to let it go. If we let it go, he did some, did you see how he moved, Kyle? So there was some work done on the desk, and there was some sounding and all that kind of stuff. So my work turned into his kinetic energy, which did some more work. Wait. Here we have a weapon of mass destruction. Okay, here we have a rubber band. How much energy is in my rubber band?
None.
I could drop this on my foot. Is anybody going to run for cover if I drop this on your foot? Yeah. Okay, so basically it has very, very little potential energy in it, but no other type of energy in it. What do I have to do to put energy into this?
Put away. Stretch it. Stretch, yeah.
When you stretch it, what are you doing? You're doing work. I apply a force over a distance, and so now I've done work, and so now it's full of
Potential energy.
potential energy, because all I have to do is let go of this, and all that potential will turn into kinetic, and I almost got two of you. That was pretty good. So, I did work on his head.
There you go.
Came from the work I did over here, right? Okay, so now that we understand this, we can talk about Minnnie Mouse. Minnnie Mouse is going to be the big point thing on the test tomorrow. So, Minnnie Mouse, she's going to go and sit on the floor, and I will sit with her because she's my friend. Can you see that? Do you need to be closer? Okay. Now, Minnnie here, she is well over 20 years old, so she's older than any of you guys. Probably older than Jake, too. I think she's probably closer to 25.
Okay.
I've had Minnnie for a long time. How much energy does she have right now?
0.
She has no energy. What do I have to do to put energy into her?
Work.
I have to do work. So you guys have all seen toys like this before. I am going to pull back on her. So I applied a force over a. So now she's full of potential energy. So when I let go, that's going to turn into kinetic energy. And she's going to go racing across the floor. And
but does that kind of work? Because you
Force over
move it
distance.
this way.
well, I did work pulling her this way, and she's doing work shoving herself that way. She's a wild driver. Now, here's the big question. Are you ready?
Yeah.
How far back did I pull her?
About a foot.
Exactly a foot. How far forward did she go?
Very far.
A lot more than a foot. Why did she go farther forward than I pulled her back?
Physics.
Now, I'm not asking what is the little mechanism inside the toy. I'm saying, did she get more work out than what I put in?
No.
Oh.
Some of you were enthusiastically saying yes, and some of you were saying no. If you were saying yes, please slap yourself. If we got more work out than what we put in, then we would be getting
Magic.
magic energy from nowhere, and we would design our cars like this. You shove your way back out of your driveway, and then you can drive your car free. And this would work out wonderfully, right? Except it can't work that way. Now, there are two factors involved in work. Force and distance. Here I had a small distance, there I had a big distance, so what must be true? I didn't understand that.
All the force going this way was larger, bigger than the force going out.
Oh, okay. So you're saying I'm pulling back with a big force in a small distance, and she pushes forward with a small force in a big distance. So that way the work out and the work in are equal because we can't get magic energy from nowhere. Okay, so. We can't get magic energy from nowhere either. Okay, this shouldn't be this hard, but come on. Papa. Thank you. Okay, now, this didn't feel like a whole lot of force when I pulled her back. So how do I know that she's really pushing forward with a small force? That was our hypothesis. Is there a way to test it? Yes, there is. This is why I got this. Okay, so if this is here, and I just let her, she's sliding. So I'm going to push down on her, increase her normal force, and hey, well, for a second there. Yeah, if I'm pretty much vertical here, I can get it to turn the wheels just a little bit. So I pretty much have to be vertical to get any wheels turning, which means the force I have to pull back with is a minimum about equal to her weight, right? So if I pull her back and I load her up with potential energy, why isn't she flying into Amanda's lap in a beautiful parabolic trajectory? Because she's a wuss. She can't push well, we just said she was pushing forward with a small force, right? So she's pushing forward with a really, come on. There we go. Really small force. Now, if you look, what is the ratio between the length and the height here? Maybe like 15 to 1, 10 to 1, somewhere in that area?
Yeah.
So if that's the case, if this is like a 15 to 1 ratio, then that means basically she was pushing forward with 1/15 of her weight. So it took a force equal or greater than her weight to pull her back, and she was only pushing forward with 15 times smaller force, so the distance must be 15 times bigger if the workout was equal to the work in. Now, in real life, we would love to think that the workout is always equal to the work in, but some of that energy that I put into this turns into sound and heat. So do I even get out as much as I put in?
No.
No, and that's the sad thing about life. You learn that you always put in more than you get out.
Deep.
No, the reason we don't design cars like this is it would work out great as long as it's downhill all the way to work. But the first time you hit an incline more than about 1 degree, you're going to say, oh, this isn't working too well. Any questions? Okay.
You want the rubber band?
No, it's just there because it's supposed to pop a wheel.
Oh, okay. I wasn't sure that was what you were saying.
Just to look